Look up at the night sky tonight, and you will see something that feels permanent. The stars have shone for as long as any human has been alive to notice them. Civilizations have risen and fallen under the same constellations. It is easy to believe that the universe simply is. Fixed, eternal, unchanging. That belief is wrong. And it has been wrong for a long time. The universe is not a photograph. It is a life, with a birth, a childhood, a prime, and eventually an end. And here is the part that should unsettle you. Astronomers now have strong evidence that the universe's most productive, most luminous, most alive period is already behind us. Not ahead of us, behind us. We are not living at the dawn of the cosmos. We are living somewhere in its long, quiet afternoon, watching the light slowly go out of the sky, one galaxy at a time. This is the story of how we figured that out, and just how far the darkness still has to go. The illusion of a frozen sky. For most of human history, change in the heavens was considered impossible, even offensive to the natural order. Aristotle taught that the stars belong to a perfect, incorruptible realm, forever fixed in their crystal spheres. When a new star appeared in 1572, what we now call a supernova, it caused a genuine philosophical crisis in Europe, because the unchanging heavens were not supposed to be capable of change at all. It took centuries to dismantle that idea. Galileo's telescope showed craters on the moon and spots on the sun, blemishes on a supposedly perfect canvas. Edmund Halley later proved that comets were not one-off, omens but recurring visitors on long orbits, returning again and again like planets on stretched-out paths. Each discovery chipped away at the idea of a static sky. But the real earthquake came in the 20th century, when astronomers realized that the entire universe itself was in motion, not just objects moving within space, but space itself stretching. Distant galaxies were found to be racing away from us, and the farther away they were, the faster they retreated. The obvious conclusion was almost too strange to accept. The universe had a beginning, and it has been expanding, changing, and evolving from that moment onward ever since. But once astronomers accepted that the universe changes, an unavoidable follow-up question emerged. If the cosmos had a beginning, does it also have a middle? And an end? To answer that, scientists needed something no telescope alone could give them. A way to compress billions of years of cosmic evolution down into something observable in a human lifetime. That tool turned out to be simulation. Building a universe inside a computer. You cannot watch a galaxy evolve. A single spiral galaxy takes roughly 200 million years just to complete one rotation. No observatory, no matter how advanced, can sit and watch that unfold in real time. So scientists cheat. They build miniature universes out of mathematics. The idea is simple in concept, even if the execution is staggeringly complex. Take the known laws of gravity, add in the physics of gas, radiation, and nuclear fusion, sprinkle in billions of particles representing stars, gas clouds, and dark matter, and then let a supercomputer calculate, one tiny time step at a time, how everything pulls on everything else. Run that forward for enough computational cycles, and you get something remarkable. A fast-forwarded movie of cosmic history compressed from 13.8 billion years down into a few weeks of processing time. Modern versions of this technique go by names like Illustrious TNG and Eagle. Massive simulation. Projects that use tens of thousands of processor cores working in parallel. These digital universes don't just look pretty. They let scientists test why the universe evolved the way it did, running the same cosmic experiment over and over with slightly different starting conditions to see which rules actually produce a universe that looks like ours. These simulated universes are not just pretty visualizations for documentaries, they are genuine scientific instruments. Researchers can pause them, rewind them, and check whether a simulated galaxy at any given moment matches what real telescopes observe at that same point in cosmic history. When a simulation synthetic universe lines up with real observational data, the sizes of galaxies, the rate at which they form stars, the way they cluster together, scientists gain confidence that the underlying physics baked into the simulation is correct. When it doesn't line up, that mismatch itself becomes a clue, pointing towards some missing ingredient or misunderstood process that still needs to be worked out. And what these simulations reveal, again and again, is a universe with a very clear life cycle. It has an infancy, a growth spurt, an adulthood, and unmistakable signs of decline. The peak of that life cycle has a name astronomers actually use: cosmic noon. Cosmic noon, the universe's greatest party. Roughly 3 billion years after the Big Bang, the universe entered its most productive era. Galaxies were closer together, gas reservoirs were still full, and mergers between galaxies were common events rather than rare spectacles. During this window, Galaxies were forming new stars at a rate more than 10 times higher than what we observe in similar galaxies today. To put that in perspective, our Milky Way currently forms only a handful of new stars each year. During cosmic noon, a galaxy of similar size could have been forming hundreds of new stars annually. If you could stand on a habitable world during that era and look up at a clear night sky, you would not see a few thousand faint pinpricks of light. You would see a sky ablaze, tens of thousands of visible stars, a shimmering band of active star-forming regions, and the occasional brilliant flare of a newly ignited quasar outshining entire galaxies put together. Observatories, like the Atacama Large Millimeter Array, ALMA, in Chile, and the Hubble Space Telescope, have peered deep enough into space, and therefore far enough back in time, to actually catch this era in action. Distant, dust-shrouded galaxies from this period appear as chaotic, irregular blobs, rather than the neat spirals and ellipses we're used to, still in the process of assembling themselves out of colliding gas clouds and merging smaller galaxies. Some of the clearest evidence for this fiery era comes from deep field surveys, projects where a telescope stares at one small, seemingly empty patch of sky for days or weeks at a time, collecting every faint photon it can. The longer the exposure, the fainter and more distant the objects that swim into view. And because light takes time to travel, the faintest, most distant galaxies are also the ones we're seeing as they existed, billions of years in the past. It's a strange kind of time machine. The deeper astronomers look into space, the further back in time they are actually looking. Surveys of this kind, carried out with instruments like the Hubble Space Telescope and more recently the James Webb Space Telescope, nothing like the calm, orderly spirals and ellipticals of today. These early systems are clumpy, irregular, often caught mid-collision, and glowing intensely in the light of newly formed, short-lived massive stars that burn hot and die young. Some of these galaxies are forming stars so quickly that astronomers have nicknamed them starburst galaxies, systems converting gas into stars at a pace that, if sustained, would exhaust their entire fuel supply within a few 100 million years, a blink of an eye on cosmic timescales. Why was this period so explosively productive? 3 ingredients came together at once. First, raw material. Early galaxies were still threaded to the wider cosmic web by filaments of gas, a kind of umbilical cord constantly. Second, collisions. The universe was smaller and denser then, meaning galaxies were packed closer together. Mergers between galaxies of similar size could trigger firestorms of starbirth, sometimes producing new stars 1,000 times faster than a quiet galaxy like ours does today. Third, dust. It sounds unglamorous, but cosmic dust, tiny grains of heavier elements forged in the death of earlier stars, is essential for star formation. Dust allows hot gas clouds to cool down efficiently enough to collapse under their own gravity. Without dust, gas simply lingers, too hot and too diffuse to ever ignite into a star. The very first generations of stars had to form without any dust at all, which is part of why astronomers still don't fully understand exactly how the earliest stars managed to ignite. But peaks, by definition, don't last, and this one didn't either. The long, slow goodbye. After cosmic noon came what some astronomers loosely call cosmic afternoon. And today, roughly 13.8 billion years after the beginning, we are living somewhere in cosmic evening. The numbers make the decline undeniable. The overall star formation rate of the universe has dropped by more than a factor of 10 since its peak. Our own Milky Way, once presumably far more active in its youth, now produces only a handful of new stars per year. Some estimates put it at fewer than 10. Multiply that across a human lifetime, and our galaxy might light up only a few hundred new stars total during the entire span of someone's life. And the Milky Way is considered comparatively healthy for a galaxy of its size and age. So what happened? Why did the universe's stellar furnace turn down? The uncomfortable answer is that the universe is, in a very real sense, running out of ingredients. Star formation is not a renewable resource on cosmic timescales. Every time a cloud of gas collapses into a new star, that material is either locked away inside the star for billions of years, or eventually recycled in smaller and smaller amounts through stellar death. Meanwhile, the accelerating expansion of the universe is steadily pulling galaxies farther apart, cutting off the filaments of fresh gas that once fed them. Less gas flowing in means less fuel available to make new stars, a slow cosmic scale drought. There's a useful way to think about this using a household budget analogy. Imagine a young galaxy as a household with a huge stockpile of savings and a steady paycheck arriving every month from outside sources, the intergalactic gas filaments. In its youth, the galaxy can spend freely, building new stars at an enormous rate, because both the stockpile and the incoming paycheck are large. But as the universe expands and filaments stretch thin, the paycheck shrinks. Eventually it stops arriving altogether. All that's left is whatever savings remain in the stockpile, and every star built from this point forward draws down that dwindling reserve a little further with no way to replenish it. That is essentially the situation most galaxies, including our own, find themselves in today. This is measurable, not just theoretical. Astronomers can trace the overall star formation history of the universe by combining observations across different distances, and therefore different cosmic time periods, into a single timeline, sometimes called the Maddow-Lilly diagram, named after the researchers who helped establish it. That diagram shows, in stark quantitative terms, a rapid rise in star formation during the universe's first few billion years, a sharp peak around cosmic noon, and then a long, steady, unmistakable decline, continuing all the way to the present day. It is one of the most direct pieces of observational proof that the universe's productive era has already passed. But starvation from a shortage of raw material is only part of the story. Some galaxies die far faster and far more violently than a simple gas shortage would suggest. For those galaxies, the killer isn't a slow famine. It's something closer to a heart attack. The anatomy of a galactic death. Astronomers use a specific, almost clinical term to describe a galaxy that has stopped forming new stars: quenching. It's an apt word. Something that was once burning bright has been extinguished, not necessarily destroyed, but silenced. Galaxies that have been fully quenched earn a nickname among astronomers that sounds like something out of a crime novel: red and dead. Red, because without hot, young blue stars being born, a galaxy's light gets dominated by old, cool, reddish stars that live for tens of billions of years. Dead, because star formation there has essentially ceased. A textbook example is the giant elliptical galaxy M87, sitting at the heart of the Virgo cluster, roughly 55 million light-years away. Unlike the Milky Way's flattened disk and elegant spiral arms, M87 is a vast, featureless ball containing several trillion stars. And almost none of them are new. Somewhere between 20 and 30% of all galaxies in the universe fall into this red and dead elliptical category, and because they can grow to such enormous sizes, they collectively house nearly 40% of all the stars that exist. So how does a galaxy go from a thriving stellar nursery to a red and dead graveyard? Researchers have identified several mechanisms, often working in combination rather than alone. Mechanism 1, stellar feedback. When a burst of star formation produces thousands of massive stars all at once, those stars generate ferocious winds and eventually supernova explosions. These events can superheat the surrounding gas or blast it out of the galaxy entirely. Either way, the fuel needed for the next generation of stars is destroyed or expelled before it can be used. Mechanism 2, environmental stripping. Galaxies are not isolated islands. Many live within enormous clusters containing hundreds or thousands of neighbors, all embedded in a thin, superheated intergalactic gas. When a galaxy plows through this hot plasma, friction can literally strip away its own reservoir of star-forming gas, like a car losing fuel through a hole in the tank while driving through a storm. Astronomers have directly photographed this process happening to real galaxies, watching long streamers of gas trail behind them as they're stripped bare, a phenomenon nicknamed jellyfish galaxies for their trailing tentacles of gas. Mechanism 3, the black hole at the center. This is arguably the most dramatic killer of all. Nearly every large galaxy harbors a supermassive black hole at its core, typically a small fraction of the galaxy's total mass, but capable of an outsized influence when it becomes active. When large amounts of gas fall toward this black hole, the resulting disk of superheated material can radiate as brightly as an entire galaxy of stars combined. Astronomers call these active phases quasars. A sufficiently powerful quasar doesn't just heat a small pocket of nearby gas, it can blast radiation and particle jets through the entire galaxy, heating gas to the point where it can never again cool down and collapse into new stars. In the most extreme cases, this process is triggered by a major merger between two galaxies of similar size, whose central black holes eventually spiral together and combine. The newly merged black hole gorges on the surrounding debris, flares into an extraordinarily bright quasar, and in doing so permanently shuts down its host galaxy's ability to make new stars, killing the galaxy from the inside, using the very fuel that should have built its future. It is a strange kind of tragedy, the same. Processes responsible for a galaxy's most spectacular growth, mergers, rapid star formation, black hole feeding, are ultimately what bring about its death. Success and destruction, in cosmic terms, often turn out to be the same event viewed at different points in time. Interestingly, astronomers have found that quenching doesn't always happen at a leisurely pace. While some galaxies fade out gradually, gently sliding from active star formation into quiet dormancy over several billion years, others appear to shut down remarkably fast, sometimes within a few 100 million years, practically overnight by cosmic standards. Surveys that catalog galaxies by color and star formation rate consistently find relatively few galaxies caught in the act of transitioning, sitting in what's sometimes called a green valley between actively star-forming blue galaxies and quenched red ones. That scarcity is itself a clue. If the transition zone were a comfortable place to linger, we'd expect to find far more galaxies there. Instead, it looks like galaxies tend to pass through that intermediate phase quickly, which suggests that once quenching begins in earnest, it proceeds rapidly and rarely reverses. There is a further wrinkle that makes this whole picture even more interesting. Quenching does not always mean permanent death. In rare cases, a quenched galaxy can be rejuvenated, typically by capturing a fresh supply of gas from a smaller companion galaxy, or by drifting through an unusually gas-rich region of space. When this happens, a red and dead galaxy can, against the odds, flicker back to life with a renewed burst of star formation. These rejuvenation events appear to be uncommon and temporary, more of a brief second wind than a genuine reversal of fate. But they're a reminder that even the universe's clearest trends still leave room for occasional surprises. Our own galaxy's appointment with decline. It would be comforting to think the Milky Way is exempt from this fate. It isn't, in roughly 4 to 5 billion years. The Milky Way is expected to collide and eventually merge with its nearest large neighbor, the Andromeda Galaxy. Long before any stars physically collide with each other, space between stars is so vast that direct stellar collisions will be exceedingly rare. The gravitational interaction between the two galaxies will scramble both of their structures beyond recognition. Spiral arms will be torn apart and reformed. Gas clouds will be shocked, compressed, and, at least for a while, triggered into a fresh, temporary burst of star formation, a final flare of activity sometimes nicknamed the resulting galaxy's last hurrah. But after that final burst, there will be nothing left to rekindle it. The merged galaxy, often given the nickname Milkomeda in popular science writing, will settle into exactly the same red and dead fate as M87, an aging elliptical, its blue and white stars replaced almost entirely by dim, long-lived red dwarfs, its star-forming gas either consumed, blown away, or heated beyond recovery. This isn't a fringe possibility. It's the default outcome, the same outcome that has already happened to a significant fraction of galaxies throughout the observable universe. The Milky Way is simply not there yet. It's worth pausing on just how strange this makes our own position in cosmic history. Right now, today, the Milky Way sits in a kind of sweet spot, old enough to have built up a rich diversity of stars, planets, and heavy elements, but not so old that it has already been quenched into a dim, red, dead elliptical. Whatever life exists on planets within our galaxy right now is living through a genuinely privileged window, a stretch of cosmic time when star formation, while diminished from its historic peak, is still very much ongoing. That window will not stay open forever, but it is not yet closed either. The invisible hand accelerating everything. If galaxy mergers, quasar outbursts, and gas stripping were the only forces at play, the universe's decline might eventually slow down or stabilize. But there's a fourth factor, one operating at the grandest scale of all, and it doesn't behave like the others. It's not slowing with time, it's speeding up. That factor is dark energy, the mysterious force behind the accelerating expansion of the universe, discovered in the late 1990s through observations of distant exploding stars called supernovae. We still don't fully understand what dark energy actually is, but we know its effect. It is steadily prying galaxies apart from one another, faster and faster, with every passing billion years. This acceleration compounds every other problem the universe already has. As galaxies are dragged farther apart, the cosmic web of gas filaments that once fed young galaxies with fresh star-forming material becomes stretched, thinned, and eventually severed entirely. Fewer mergers occur. Less new fuel arrives. The universe's overall rate of star formation, already well past its peak, continues its slide with no real prospect of recovery. Some astronomers have described this compounding decline using an unsettling medical analogy. If dark energy-driven expansion is like a terminal illness, then the drop-off from cosmic noon is the point at which the diagnosis became irreversible. The patient, the universe, as an active, star-forming system, is not dying suddenly. It's fading, slowly and systematically, over timescales so vast that slow barely captures it. A guided tour of what comes next. So, if we are already past the universe's prime, what does the rest of its life actually look like? Astrophysicists have mapped out this future in almost absurd detail, using known physics to project forward across timescales that make the current age of the universe look like a single second. In about 100 billion years, roughly 7 times the current age of the universe, The accelerating expansion will have carried every galaxy not already gravitationally bound to our own local group beyond the cosmic horizon. Any future astronomer looking outward will see only darkness where other galaxies used to be, their light stretched and redshifted into undetectability. From the inside, it may look as though our galaxy cluster is the entire universe. In roughly 1 trillion years, the merged remnant of the Milky Way, Andromeda, and their smaller companion galaxies will have long since finished forming any new stars altogether, gradually dominated by small, dim, long-lived red dwarf stars, the only kind of star capable of surviving for such spans of time. Sun-like stars and anything larger will have already burned out. Somewhere between 10 and 100 trillion years from now, the last new star in the observable universe will be born, most likely the product of a rare random collision between 2 failed stars called brown dwarfs, just barely producing enough compressed mass to ignite fusion. After that, no more new starlight, ever. By around 10 to the 20th power years, a number so large it's easier to write than to imagine, galaxies themselves will have essentially dissolved. Random gravitational encounters between stars will eject most objects out into the empty void between galaxies, while a smaller fraction spiral inward and are ultimately consumed by the central supermassive black hole. Around 10 to the 100th power years, even black holes will not survive. Through an extraordinarily slow quantum process known as Hawking radiation, black holes gradually leak away their mass as faint radiation, eventually evaporating entirely. Even the largest supermassive black holes in the universe. And in the most distant, speculative timescales imaginable, numbers so large that conventional notation barely functions. Some theoretical models suggest that even ordinary matter will not be permanent. Protons themselves may eventually decay, and through processes involving quantum tunneling, even the coldest, densest remnants of matter could theoretically break apart, leaving behind nothing but an extremely thin, extremely cold sea of fundamental particles and radiation spread across a universe that has expanded beyond any meaningful concept of distance. This hypothetical endpoint even has a name: the heat death of the universe, a state of maximum entropy where no more energy differences exist to drive any kind of process, reaction, or change. No stars, no chemistry, no motion. In any meaningful sense, just an eternal, silent, cold equilibrium. Why this isn't actually a reason to panic. It would be easy to end a story like this on a note of dread. But there's an important perspective that gets lost in these staggering numbers. We are still living in the extraordinarily early chapters of the universe's total story. Consider the numbers again. Even the most conservative estimates put the last possible star formation happening trillions of years from now, and the truly final dissolution of matter itself, potentially occurring at timescales so enormous that our current 13.8 billion-year-old universe represents a fraction so small it's difficult to express in ordinary language. If the entire lifespan of the universe were compressed into a single calendar year, the current moment, right now, today, would fall somewhere in the first fraction of a second after midnight on January 1st. We are not watching the final act of a play. We are watching the opening scene. The decline astronomers describe from cosmic noon is real, but it's also relative. The universe is still forming new stars today. Our own sun, only 4.6 billion years old, still has roughly 5 billion years of stable fusion ahead of it. Plenty of time for entire civilizations, if they exist, to rise, explore, and potentially even find ways of prolonging their own survival far beyond what their home star allows. There's also a kind of quiet optimism buried in the physics itself. As the universe ages and enriches itself with heavier elements forged inside dying stars, entirely new kinds of stars, smaller, cooler, capable of burning far more efficiently than anything that exists today, will become possible. Red dwarfs, the most common and longest-lived stars in the universe, are only just beginning their multi-trillion-year lifespans. In some very real sense, the golden age of small, stable, long-burning stars is still ahead of us, not behind us. The takeaway. So, is the universe already ending? In the sense that its most explosively active star-forming period has already passed? Yes. Cosmic noon came and went in the first few billion years of cosmic history, and every observation we have confirms that the universe's overall brightness and productivity has been quietly fading ever since. But ending implies an imminent conclusion, and nothing about the timescales involved supports that. The universe isn't collapsing, it's aging. Gracefully, gradually, across a canvas of time so vast that human civilization, human history, and even the entire existence of Earth's biosphere would barely register as a passing moment within it. Perhaps the most honest way to describe our current cosmic era is this. We exist in the universe's early evening. The brightest hours of the day are behind us, but the night is still impossibly far away, and there is still an enormous amount of beauty, starbirth, and possibility left in the hours in between. The lights are dimming, but they are nowhere near out.